Okay, I can move to chapter 6, motion. In the last chapter, we considered the initial position large x and the final position small x of a material particle. The motion of the particle from large x to small x is a continuous process. This continuity is expressed with the parameter t representing time as this way. So it's working, okay. So both small x and large x is a function of time and mutual positions. See, small x I would say this is constant. This is constant. So this is more like x1, x2, x3. And time doesn't matter. But this is not constant. Small x, okay, anyway. Material derivative. In the motion of continuous media, the time rates of changes of field quantities associated with the material particles play an important role. Time rates of changes of field quantities. Field quantities associated with the material particle play an important role. Let A, the component of the tensor field, what is tensor field, be a function of material coordinates x alpha and time. The material derivative or substantial derivative of A is defined as substantial material derivative. Substantial, this is material. I think one of the meaning of because this comes from substance. So substance is material. Material derivative of A is defined as dA dt is A dot is limiting A is material coordinate is fixed. Only the time change. So this is a partial derivative with time. Yeah. Where x stands for x1, x2, x3. If A is a function of spatial coordinate small x and time t, we have this goes like this. See, if you fix x you fix large x. Here you fix large x, but small x may change this much. This is a change in small x. Then the t also change. So you have this. You have this extra term. It is a little bit strange. How do you say it? Anyway, okay. So this is something like this. It's complicated. I'm sorry for this complication. The first time you fix small x, second time you fix large x. Anyway, okay. Then don't forget that I is repeated. This I is repeated. So I is a summation. So don't forget about it. The time derivative of small x with the material coordinates fixed is called a particle. Is called a velocity of particle. Velocity of particle. Okay, so then with this, for any tensor valued function a, we have partial a, partial t, v dot v dotted with gradient a. Interesting, right? But I think here something like a is x, small x is fixed. Yeah. Then here large x is fixed. Am I right? Large x t is fixed. The first one is small x is fixed. In the preceding equation, the first term represents the change in a that is due to the change in time at a fixed spatial position. The second term represents the change that is due to the change in x with time. The first term is called the local rate of change, and the second term, the convective rate of change. Sum and products of two functions, a and b of a. This is just a regular thing. The acceleration a of a particle is defined as a time derivative of v dot, which is partial v partial t plus v dot gradient v, where v is function of small x and t, equal partial v partial t if v is a function of large x and t. If we know the mth material derivative, we can find m plus 1th by the relation. This is same. Some terminology. At a special point x, if v equals 0, that point is called stagnation point. If a point x, if at a point x the velocity v does not explicitly depend on time, that is v equal v function of x, the motion is called steady. However, if we express small x in terms of large x and t, we find v equal v as a function of small x, which is also as a function of large x and t, with t appearing explicitly. A particle that was at x at time equal time t equals 0 is called particle x. It's very strange. What do you mean? If we express small x in terms of large x and t, we found with t appearing explicitly. Yeah. Maybe this is okay. I think this is maybe like this. You have x, x1, x2, then you have one point to another point. And then, for example, this is t equals 0, this is t equals t. But if you see this time, if you see in spatial coordinate, x1, this is just one point, t equals 0 to t, same point. So here, both x and t change. And t change. But small x doesn't change with t. A particle that was at large x at time t equals 0 is called particle x. Path line. So something happened. A path line is a curve traversed by a particle x as time t varies. It has parametric equation. Okay, small x equal x as a function of large x and t. X alpha is fixed. Alpha minus infinity. T is between minus infinity and infinity, where velocity field is given as vi equal vi as a function of x and t. The path line can be obtained by solving differential system. dxi dt equal vi, xi t equals 0 is x alpha delta alpha I. Does it make sense? It's a little bit confusing. Path line, streamline, and streak. Figure 6.1, the curve on the left shows the path of the particle as time varies. Streamline at a given time t. The curve tangential to the velocity vector are called streamline. That is dx equal kv, or dx1 divided by v1, dx2 divided by v2, dx3 divided by v3. Obviously, at a given time, there is no velocity normal to the streamline. In figure 6.1, the middle diagram shows a streamline with tangential velocity vectors. Streak line. Streak line is a curve representing the locus of material particles at time t and would pass through or would have passed through a given point x star. The particle that will be at x star small at some time tau is identified as something. The parameter tau traverse from the past to the future. We collect all the particles that would ever visit x star. Their location at a particular time t is obtained as something. In figure 6.1, the curve AB represents the location of the particle at time t that would pass through x star at time. This is not so easy. I'm sorry. Unfortunately, this is not so easy. Let me see. Let me go through how many pages we have in chapter 6. Oh my god, we have lots of sections in chapter 6. Oh my god, oh my god, oh my god. How many things? This is exercise. Okay. 88. Let me see. Let me think about it a little bit. Okay, so give me some time. So let me stop this video here. Then I will think about it. I will think about how I can handle this. Let me see. of things, lot of things, lots of things, lots of things. A lot of things. Okay, so let me stop it.